should be presented by Humberto Bustins. We see his name at least here as editor-chief of Axioms, but we don't see Humberto here. A few days ago, unfortunately, he got some health problems, which has not allowed him to come here. So allow me at least to pass his best regards to everybody here. Then, of course, there was question what to do with this. Always problem for organizers. But the best choice was a lecture should be the same, but who will present it? The closest person from scientific point of view to Humberto, and we have him here, Javier Fernandez. When we think on his career, so the major part of Javier's life is related somehow to Humberto. So there is no doubt that he is really very suitable person for presenting what Humberto was aiming to present. Maybe I can recall what is the title of his lecture. From Choquet integral to Choquet function, from Choquet inspired to Choquet functional integral. I remember when we have started with Humberto and with Bernard and so to work on this Choquet inspired integrals, and now I am glad to see that it has expansion further. To recall maybe some information concerning Javier. Sorry, I should change my glasses. So he studied in Zaragoza, then in Bilbao, has passed postdoctoral research stays in France, in Paris, in Lyon, and so on and so on. If we want to have some bibliographic data, in Scopus, 175 documents, almost 5,000 citations, age index 33, and so on and so on. But I think this is not important. Important is the person of Javier. I have heard him many times to present lectures and so on. I was always very glad and happy with his presentations. So now it will be passed to everybody of us which are here. So Javier, please, it's your turn, or you have it already.
Okay. Thank you very much. Okay, for the presentation, Radko. I am very happy on one side to be here, but very sad that Humberto cannot be here. So what I am going to do is to make the presentation that Humberto has prepared. Okay, it's exactly his presentation. And for that reason, whatever is good here is his work in the presentation, and whatever mistake, whatever can happen, which is not so good, is my fault. Okay, that's clear. Fortunately, Bernard, there was internet in Santa Mamiñe cave. Okay, so the presentation arrived in time. It was not easy, but we get it. And what's the idea of this presentation? Okay, here we are going to discuss some of the topics in which Humberto has been working these last years. Okay, the idea is not to present very deep results. The idea, even if there are going to be a lot of mathematical results, the idea is not going either to go into every detail, but to provide a motivation to understand why for Humberto, for all of us, this research is important, okay? And also to understand why we think it can open a new way of making research, okay? So to start, basically, we are going to speak about fusion of information. And all of us know that a very useful tool for the fusion of information are aggregation functions. Especially among aggregation functions, we are interested in fuzzy integrals. All of us know fuzzy integrals, but we can generalize them. In fact, in the last years in our group, led by Humberto, we have made several different generalizations of fuzzy integrals, especially of the Choquet and Sugeno integral. Okay? We have just modified the operations. We have considered the introduction of dissimilarities, etc., just to try to get more flexibility in order to use these operators. But there is something we have not modified. the use of the measure. Okay? Fuzzy integrals rely very heavily on the measure. But from the point of view of the applications, the measure is a problem. Why? Because building it can be very complicated computationally. And moreover, to find an appropriate measure for a given problem can be extremely difficult. As Bernard said on Monday, okay, we always say, okay, the expert is going to provide the measure, but at the end, who is the expert? Okay, how can we get this? So the idea of these extensions I am going to discuss in this presentation is, can we try to do something similar to the fuzzy integrals, but replacing the measure for something else? I am not going to find something which is the solution for the problem. In fact, what is going to happen, I am sorry, I am going to just tell the end in some sense. I am going to modify the problem of the parameters in the measure, moving it to the problem of finding appropriate functions. But at least I am going to try to convince you that maybe this is an approach that can work, okay? At the end of the presentation, I will discuss some small applications, very briefly, okay? Just to show you that actually it can work, okay? So the idea, as I have said, is to build operators which are inspired in fuzzy integrals, and specifically in this case, in shocked integrals, but trying to avoid the problem of building the measure, okay? Trying to replace the measure by a function that in some sense can provide the same value that the measure is providing to the integral, okay, but in a different way, okay? In an easiest way to find, in such a way that we can use more or less any function. So we are not so constrained by the fact that we need to have some specific properties, et cetera, to define these operators. So basically, this is notation. We use it, okay? You know, we need to order the inputs whenever we deal with the fuzzy integral. We all know what is an aggregation function. We all know what is an operator. It's just to fix some notation. And we are going also to recall, because I am going to use it at some specific point, what is the definition of overlap and grouping functions? Just functions to determine how the data either overlap between them, okay, and how they join to each other somehow, okay? And these functions are interesting because they are not associative, okay, in principle. And the functions that we are trying to recover, that we expect to recover from the shocked integral, are not going to be associative, okay? So in some sense, these are test functions to check what are we doing, okay? That's why this definition is here. And of course, we all know the definition of the shocked integral or of a fuzzy measure. Well, for the fuzzy measure, I insist the problem is that building it and finding the correct one can be really complicated. Okay, so what we are going to do is to say, okay, how is the integral working with the measure? As you can see, basically, I am considering two elements and multiplying it by the measure of an appropriate set. What I am going to do is to replace that measure by a function. The function in this first step, okay, is going to have n minus 2 arguments. I mean, I am going to consider all the inputs except the two ones involved in the difference. Okay, that's the point. In this way, we will see if we somehow recover some of the properties of the shocked integral. Okay? Observe that I am not putting any kind of restriction to the function f. This is the point. We want to avoid the complications linked to the measure. Okay? In this way, we are avoiding them. Of course, this in principle is not even an integral. Even if we call it shocked inspired, it's not an integral. It's just a function. And the question is, does all this make sense? Okay? Does it work somehow? First of all, observe that clearly the function is well defined, even if we have inputs which are the same. Okay, there are no problems. The definition is correct. Using the symmetry avoids any problem in this definition. Okay, and there, I insist, there are no restrictions on f apart from the monotonicity, which is something we are expecting. Okay, just following the same model that we have with the measures in the case of the Schottky integral, okay, and the symmetry. The symmetry can be dropped, okay? The symmetry is not strictly necessary. We can work all this without the symmetry, but in some points, things become a bit more complicated, okay? That's why I am going to consider the symmetry and avoid these technical difficulties, okay? First of all, observe that we can rewrite the expression of this Schottky-inspired function in this way, okay? We have just rewritten the terms, and the interesting thing is that we observe that we are recovering convex combination the inputs. That's nothing extremely new, but at least it's providing us with an idea of which is the structure behind these functions. Well, let's try some simple examples, okay? First of all, the definition, the original definition starts with the smallest element. Maybe we can try to do a similar definition starting with any other element, okay? This leads to this definition. In particular, in this way, we can recover one of the order statistics, okay? However, we are not going to follow this. Recall that the idea is not to provide a mathematical study. The idea is to use these functions, okay, in the same way as we use Schottky integrals. And Schottky integrals are aggregation functions, okay? Maybe we are not going to recover aggregation functions, but at least what we're going to recover are the boundary conditions, okay? So at least what we want to have is that we are not going out from the interval 0, 1, which is where we are going to work. That's why we are not going to consider this approach. But it's a possible way of researching if this can lead to something interesting in some settings, etc. It's something we are also exploring, and it can be of interest. Okay, let's consider some simple example. And the easiest example we can consider for the function f is a constant function. Okay, and what happens if we consider a constant function? That we recover convex combination, the minimum and the maximum. This result, this example, seems very simple, but for us it's very relevant. Why? In our group, there was a thesis made by Josu Rodriguez, who was here 2 years ago, okay, presenting some of the results, when we saw that in some neural networks, for instance, instead of considering all the data, you can just consider the smallest and the biggest data. Okay, so the possibility of reducing your data to consider just some subset of them, which reflects which are the smallest values and which are the biggest values, is interesting to reduce the computational complexity of those neural networks. And for that reason, this kind of results for us, from the point of view of possible applications, are relevant. And observe that we are getting this result directly from the easiest possible example. Okay. Of course, things can become a bit more complicated. Just let's consider dimension 4. Let's consider any function as, for instance, the mean. Okay. And as you can see, what we get is this expression here. Again, is getting a kind of mean between the smallest and the biggest value, where the weights are provided by the intermediate values. Okay? Again, this can be from the point of view of the applications to reduce the complexity. Okay? That's why all these results are very interesting for us. Okay? Well, what about the properties of these operators? Clearly, if f is symmetric and increasing, which are the properties that we have demanded from the very beginning, the resulting function, the resulting Schottky-inspired function, is symmetric. Perfect. That's very easy. And moreover, we recover an idempotent aggregation function. Okay? So in this sense, this extension is not, let's say, providing something strange. It's providing what we were expecting, somehow. Okay? I insist, it is not a Fuzzy integral. It is not an integral. So it seems that at least since we are recovering aggregation functions, we are able to recover a technique that maybe can be useful for more data. Let's continue. Okay, what about the continuity? Continuity is relevant in the application. Maybe it's not so relevant sometimes from the point of view of the theory. Okay, clearly, if everything is continuous, the resulting function is continuous. But here we don't have an if and only if. First of all, it is clear that if the function f is not continuous and we are not imposing restrictions on f, this is critical. Okay, because from the point of view of applications, in some applications, continuity cannot be a good idea. Okay, in that sense, we don't recover a function which is continuous. So we don't know for the moment if the Schottky-inspired function is continuous if and only if f is continuous. Okay, this is an open problem from the mathematical point of view, or which the condition should be at to the function f. Okay, now let's look to what we recover. Actually, we are going to recover some properties which are also true when we are using measures. Okay, so in this sense, again, we are not going to get some very surprising results. But again, this is a good thing. We don't want to be so far from fuzzy integrals, from the Schottky integral. Okay, in principle, later, yes, later we will go further and further. Okay, but in principle, we don't want to create something which is absolutely different from the Schottky integral. And for instance, one first property that we have is that if we consider two functions, f1 and f2, and we consider a convex combination, okay, what we recover is that the Schottky-inspired based on the convex combination is the convex combination of the Schottky-inspired. That is, we have some linearity, okay, some convexity that is providing a structure which is nice for the applications, okay, especially for parameterizing. Moreover, this extends even to a weighting vector. So we recover linearity with respect to the function f. So our space of f functions used for defining the Schottky-inspired function, okay, has some linear structure that makes, let's say, easier to work with it. Okay, we are not dealing with something absolutely strange. Right. And we want to see which is the relationship with the Schottky integral. So we are going to analyze some properties related to the usual Schottky integral, plus homogeneity and shift invariance. Here we have some problem, let's say. Okay, observe that we recover homogeneity if and only if the function f is continuous, is constant. Okay, this is telling us that our operator is not going to recover all fuzzy measures, all Schottky integrals. Okay, in fact, it is telling us something more. It is telling us that the class of Schottky-inspired functions intersects with the class of Schottky integrals, but they are different classes of functions. So we are doing something different. Okay, and this is interesting. This is interesting because it means that actually what we are doing, okay, makes sense. I am trying to convince you that it makes sense. Okay, but it's providing us with new tools. Okay, new operators. Okay, with respect to the shift invariance, the result is just that whenever the f preserves in that way the shifting, okay, we recover the shift invariance. The key point here is that fact that we only recover homogeneity when the function f is constant. Okay, let's continue. Oh, sorry. It has stopped. Now, okay, we can also see that we preserve this linearity, okay, just using the previous properties. This extends directly from the previous case, okay, and we can also say something about duality, okay. The result is just a calculation, okay, but we see that again the preservation of duality is more or less natural, something that we could expect. If you can see, probably the only result which was not so expected is the one about homogeneity in principle, okay, because we need to require the function f to be constant. And with respect to the duality, this result, but if we consider again this example, what we are going to see is how we can use very well-known functions to recover. We have proved with constants. The constants have provided us with some good results. what happens if we consider order statistics of the function f. Okay, the result is what you have here. Okay, as you can see, again, the expression that we get is not so complicated. But the interesting point about this example of the use of the order statistics is not the example by itself. Okay, it's the fact that we can use all this just to generalize, to make the calculation, and to apply to the case when f is an OA operator. Because what is an OA? A linear combination of order statistics. We have seen that our operators preserve this linearity, so we can use it to determine which is exactly the expression that we get for the OA. Okay, so this allows us to include the OAs here to define the Schocket-inspired function. And this is the interest of this. The problem of the Schocket-inspired function, the problem of the function f, is that actually it's not taking into account the ordering of the elements, not completely. Okay, but if what we are using is an operator, then we are taking that into account specifically. Okay, so this fact that the ordering of the elements can be taken into account in the definition can be considered by means of the OA. Okay, and we get an expression which is perfectly manageable. Okay, which is not complicated to apply because the expression that we get there is not complicated to obtain. And I have told before that I introduce the overlap and grouping functions, okay, just as test functions. Why test functions? Because we want to see if we can recover this kind of functions somehow. Okay, just an examples. I mean, it's not just because they are especially important in this case or because we want to do something very relevant. Just to see, can we recover other functions? Okay, how? What do we get? And the results are these ones. With respect to overlap functions, we recover them if and only if the function f is an overlap, is zero, is identically zero. Okay, that means that in that case, the only overlap function that we are able to recover by means of a Schocket-inspired function is the minimum. Okay, it's the only possible one. This can be seen as something limiting the results, but on the other side, it's also telling us that we are not covering so many aggregation functions. Again, we have a new class of aggregation functions that has not been completely covered by the things that we have already studied. Okay, that's interesting. And with respect to grouping functions, the conditions are a bit different. Okay, in this case, there are a bigger variety of functions f that provide a grouping function. Okay, it's not that we are always restricted to have a constant everywhere. No. Okay, in some cases, in this case, the function f needs not be a constant. And this is telling us again that we are not just dealing with something in which the only interesting examples correspond to f constant or something like that. We can recover aggregation functions, even aggregation functions so closely related to one to another as the overlap and grouping because they are dual. Okay, in this case, they are obtained from different point of views. Okay, and it's said that we cannot recover in general Schocket integrals, but what we can do is to use a measure to define the function f. Okay, and in this way, we are to recover at least some specific cases of Schocket integrals. Okay, but I insist, we do not recover all the Schocket integrals. Schocket-inspired integrals do not contain all the Schocket integrals. Okay, there are Schocket integrals we cannot cover at all. In this way, we can make a trick to recover some of them. Okay, and in this way, moreover, if we find a function f which seems to work, or if we find a measure which seems to work, we can try to translate into the other setting. Okay, so it seems that up to now, we have introduced a family of functions. Okay, and in principle, it seems to be a good idea in the sense that we are providing something which has not been covered by other classes of functions. Okay, the idea is simple. Okay, the possibility of using any function f means that we are not constrained to very strict conditions that can be the case of fuzzy measures. But what else can we do? Okay, if we try just, well, these are different references, okay? What else can we try to do in order to get even more generality? Again, we need to choose the function f, but we are choosing the same function f for all the terms. Okay? Well, we can say, yes, in the Schottky integral, we use the same measure for all the terms. That's true. But if we are trying to avoid restrictions, why cannot we consider a different function f for each different term? Okay? What happens in this case? Of course, this case, in principle, would cover the previous one, but I am going to make a modification. Okay? We are going to make here a change so that we are not going to do just considering different terms in the previous definition. And what is this difference? Okay. The idea is that in the previous case, the function f has all the time, okay, the same number of variables. When we consider the measure, okay, for each of the terms, the set that we are measuring has a different ordinal. Okay, so if we're going to replace the function f by multiple different functions f, fi, okay, what we can try to do is to say, hey, maybe we should do that these functions act on different sets of variables. Okay, they are not going to have the same number of variables. No, for each term, they are going to act exactly over the same inputs that the measure would consider. That's why here, as you can see, I am defining a family of functions, okay, which takes exactly each of them I inputs. Okay, and observe that here I am just asking that they are Fashion functions. I mean, this is just a function with preserve the boundary conditions. In 0, it's 0. In 1, it's 1. Okay, just a sort for that. And then we can provide this definition. Okay, here the permutation is denoted by sigma, just to avoid some complication with all the other indices and all that. Okay, but observe that what we do is instead of one single f, we consider a different function f for each term, but it is acting exactly on the inputs that the measure would consider. Okay, it's a different approach. Okay, it's not just copying what we had before. Okay, it's something different. And the question again is the same. Does all this make sense? Can all this work? Let's see. First of all, we have these remarks, but what is relevant is that the functions f actually can be seen that they are not necessarily defined over the whole unity per cube, okay, but rather on one substructure. Okay, this can be relevant later for some examples. This is relevant also for analysis, but in this point, it's not something I am going to stop, okay? Just recall that at the end, I can work in this set below, okay? So I can consider always that the first element of the inputs is different from 0, because when the elements are 0, if the first element after ordering are 0, then all those terms are not going to appear in the integral, okay? So I can ignore them. So it's something which simplifies the calculations. Okay, again, if we start with the easiest examples, let's consider that f is equal to 1, fi is equal to 1 all the time, constant, the same function everywhere, and of fy is equal to 0 in the other case. Then we recover the minimum at the maximum. And this is obvious. This is something that should happen. Because in this case, if all the fi are equal to a constant, we are exactly in the same situation as before. Okay, there's no difference. So we should recover what we had before. Okay? Things become more interesting when we choose for each fi a different constant. Okay? Again, all of them are constants, but all of them are different constants. This is not covered by the previous case, by the Schottky inspired function. Okay? This is something which is slightly different. And in this way, we can recover our operators. It's interesting. Okay? Because our operators are particular cases of the Schottky integral. And we are showing that these specific cases of the Schottky integral are recovered from our definition. Maybe it's not so surprising. The end of definition is very general. Okay? Clearly. But it seems, again, that the definition makes sense. So this we are recovering partially, okay, the Schocket integral, which is something that tells us that the idea which is behind all this research makes some sense. If we consider its function fi as, for instance, a particularization for some specific subset of interest, let's say the maximum of the indices, just starting from I, okay, what we get is that the functions that we get are very easy to compute. Again, theoretically, this is quite trivial. From the point of view of applications, this is very interesting. Because recall that the main motivation behind all this study, or one of the main motivations, was to reduce the complexity of those processes where we need to use the Schocket integral, or we want to use the Schocket integral. Okay, and here the complexity is reduced quite significantly. Okay, by choosing functions that can be almost anything. Well, not anything, but something easy to handle. No. Again, the result I have commented before, if some of the inputs are equal to 0, okay, we can ignore all the previous terms. Again, this simplifies the calculations. Again, this is very relevant, for instance, when we have to make the fusion of many data. Because in many problems, for instance, when we are using deep learning, in many times, we have a lot of zeros. Okay? The fact that we have a lot of zeros and it allows us to ignore all those terms directly simplifies the calculation again, make the things easier. And again, we only need to worry about how to define the functions for those terms which are not 0. Okay? In the case of the measure, we need the whole measure. Here, no. Here, we only need the functions for the terms that we are going to use. Okay? That's why, again, this suggests that this can be an interesting approach. Of course, we have the symmetry, nothing relevant. But for instance, we have also this result that, again, can be, let's say, provide a way of calculating these functions in a way which can be simple, easier in some cases. Okay, this is just a rewriting of the integral as we did before for the Schocket inspired. Okay, and using this we can prove all these properties very easily. Okay, of course we have the boundary conditions. Okay, of course we have idempotency. That's a good thing. Okay, and what we have is that, well, is between 0 and 1, it's perfectly well defined. Okay, and in the case, a specific case, in which we take the list of the functions equal to 1, only the last one. I am not telling that all of them are equal to 1, it's only the last one equal to 1, then I recover perfectly idempotency. Okay, and the restriction, I mean, it's not complicated. Since we have all the other functions to play with, we are just allowing us to have less restrictions to deal with these functions. Okay, in the previous case, when we need to prove, let's say, homogeneity, for instance, we have the problem that, okay, the restriction was so hard that it was limiting very hard what we can do. Here, in order to get, for instance, idempotency, the only thing that we need to do is just to fix the last function. All the other ones, they can be whatever. Perfect. Well, I am going to introduce some more notation just to simplify some of the results that we are using here. Okay, just to avoid writing all the time these tuples, these I tuples. Okay. And basically, there is something that we can ask. Think again in the Schocket integral. Imagine that I have applied the Schocket integral, and I know that the Schocket integral for some specific problem has worked properly. Then I am interested in knowing which is the measure. Of course, you will tell me, if you have used the Schocket integral, you know the measure. But even you are providing the results, and you are told, we have used here a Schocket integral, but you are not told which is the measure. To recover the measure can be complicated, and that can be interesting for the application. Okay? Because in some cases, maybe you know which is the result that you want. Okay? But you don't know how to get it through the Schocket integral. This is the question that we are answering here. Imagine that we know the result. Imagine that in an application, we know what we want to get. Can we recover the functions? The answer is yes. And again, because I only need n functions without further structure. Okay. The problem with the measure is that the measure has a structure apart from the result that the Schottky integral is providing us. But here, I don't have that structure. So in this case, it's very easy to recover the functions. Here, we have a first hint that this generalization, this approach, okay, can be interesting in the applications, can be useful, more than interesting, useful in the applications, because once you know which are the good results to get, you can try to get what are the functions providing those results. And then you can try to translate them to other instances, to other settings, to see if actually they work, okay, or it's just by hazard that it has worked in some data set and not in another one, okay? But this is something you cannot do, in principle at least, with the Schottky integral. Here, you have how you recover everything, okay? As you can see, you recover it in a unique way, okay? This is relevant because you are not forced to make any choice. If you know the results, you know which are the functions that you need to use, okay? So if you know the results, you know which is the Schottky functional that has led you to these results, and you can try to recover directly the operator to go to another setting. Let's continue. Again, we want to see which is the relation with the Schottky. And what we see is that idempotency, we have already discussed it, okay, and the boundary conditions are always set, no problem, okay, and again, we have some restriction with respect to the homogeneity, but the restriction is not, in principle, not so terrible as in the previous case, okay? In the previous Schottky inspired, the function should be constant. Here, we are asking the functions to be zero homogeneous. Actually, the problem is that, obviously, if the functions are constant, okay, then it's going to, well, sorry, this is monotonicity. Just a second, here. Probably here we are going to have a problem similar to the previous one. Okay, at the end, we are need to be reduced to the case of constant functions, but that's something we have not proved at the moment. Okay, maybe there is some property that we are losing somehow. Well, with respect to monotonicity, okay, if we define increasingness for the vector of functions in that way over there, in that equation 9, okay, observe that we are comparing functions of different inputs, but we can compare them in that way. Well, as long as the function, the Schottky functional integral is increasing, it follows, okay, that also the vector f should be increasing. Okay, but in principle, we don't have the if and only if. Okay, we cannot say that if the functions are increasing, if the vector is increasing, then automatically the Schottky functional integral is also increasing. Moreover, we can consider this example. In this example, what we have is a function, a vector, okay, which is just the first element. Recall that from the definition, we can assume that T1 is different from 0, so there is no problem defining this example. Okay, and what we see is that the function f, the vector f, sorry, is increasing, but the resulting Schottky functional integral is increasing, but the first function is not increasing in the usual sense. Okay, so the relation between the increasingness of the vector and the increasingness of each of the functions is not so clear. Okay, it's not that, okay, we translate one to another and no. Here, there are some things that need to be explored. There are some points that can be interesting to analyze. Okay, I'm not going to enter into the details. Okay, of course, we have this result again, saying that if all the functions are increasing, of course, what we recover is increasing. But we are recovering increasingness even if this is not the case. We don't have, in principle, a full result on increasingness. Okay, a full characterization of increasingness for this kind of Schottky functional operators. Well, with respect to shift invariance, okay, this is the result. Again, what we are asking is that each of the functions fi are just constant when we are adding something and we are not going out from the domain. Okay, so I go a bit faster. And we recover monotonicity, okay, in this case. Well, so if all the functions are constant, then my function is comonoton additive. And again, this seems to be too restrictive. If one wants to recover, in general, all Schottky integrals, well, we can only use functions which are constant. But obviously, if we are using functions which are constant, in principle, we don't need to recover all the fast integrals. Okay, because observe that we fix the vector of functions. In other words, in principle, there are Schottky integrals that do not fall into the scope of this class of Schottky functions. Okay, but again, at least some of them are going to enter here. Okay, and again, we can ask ourselves, can we do something else? And here, what we are going to do is something, okay, that we have done already in previous works. Okay, we have explored how to change the measure by other functions. Something that we have made in other modifications of the operator, of the Schottky integral, was to consider also a different way of comparing the inputs. When you have this difference at the beginning of the definition, okay, it's the summatory of the differences times the measure, you can consider this measure, this difference, in terms of a dissimilarity function. Okay, this led in our case to the Schottky integrals, and here we can try to do exactly the same thing, just that one. Okay, I am going to go this part faster because I see that I don't have so much time. Okay, but of course, we can apply this idea to all that we have done to here. Because up to here, we have worked with the part of the measure, but we have not considered the part of the difference. Can we get something new, something better, if we also consider this part? Because in this way, the relationship between the inputs can be taken into account in two different ways. On the one hand, by the functions, and on the other hand, by the way I decide to compare them. Okay? And maybe this combination can lead to something interesting. Just to recall, these are examples of restricted dissimilarity functions, basically, that are telling me if two elements are equal, two elements are completely different, or how different they are. Okay, I'm not going to enter too much in the details. Okay, and what I can do is to move the Schottky-inspired function, okay, to the, let's call it the Schottky-inspired functions, replacing the difference by the dissimilarity. Okay, observe that I am going back to the first definition of Schottky-inspired. We can do exactly the same, okay, with the Schottky functional, the one in which I am using a different term for each of a different function for each of the terms. I am not going to enter into the presentation because it's quite long otherwise, okay? I am just going to focus on this one because it's the one we have used in the case of the applications I am going to speak at the very end. Okay, for instance, this is an example, okay? This is another example, okay? The key point, again, is that it doesn't matter which is the size of the inputs. The relevant thing is that, again, we are getting all the information in terms of the smallest and the biggest. And this, as I have told you at the beginning, is relevant for us because we know that in many times this information is enough and should be enough. We have proved that in other works. Okay? So this is something that can be, that tell us that this can be of interest. Okay? Well, we have this result telling us that we recover a function recall just the boundary conditions. Okay? That in 0 it takes the value 0 and in 1 it takes the value 1. When we have one of all these conditions. The first condition is very, very, very restrictive. Okay? In general, the other ones are just depending on D, but the first condition is very restrictive. Okay, so the first condition usually is something we are not going to use because even for a strictly monotone function, it does not work. Okay, but it's good to have it there. Okay, it's good not to depend only on the dissimilarity that we have introduced, but also on what conditions we can impose to the different functions. Here are some more examples, but I go a bit here, some properties. Again, more or less, they are the same properties that we had in the previous cases, okay? We are just changing the difference via the similarity, okay? Observe that here we are not recovering aggregation functions, but pre-aggregation functions, functions that are increasing in one direction, okay? Not in all the directions of the first quadrant, okay? That's relevant. But apart from that, basically, we are recovering, well, results that are more or less natural. We are not recovering something which seems to be so different, okay? But again, we are having a bit more flexibility. The fact that we are having the dissimilarity provides this flexibility because in some situations, we know how to compare data. Well, we know how to expect the comparison of data B, and we are expecting that the data are not equivalent to each other. Okay, and the dissimilarity allows us to introduce this information in the definition of the functional. What? Then we recover averaging functions in terms of the conditions of the dissimilarity. Again, we do not recover increasingness if some of the functions are not increasing. These are properties similar to the previous ones. Okay, additive invariance, homogeneity, the standard results. Okay, I'm not going to focus very much on all this, okay? To recover an aggregation function, what we need to impose is this one Lipschitz condition in each of the components of the dissimilarity, okay? It's the dissimilarity which determines if we recover an aggregation function because it's the dissimilarity that can force or can make you lose the appropriate increasingness, okay? So that in the dissimilarity hence has a real relevant paper here, okay? And observe that to have it, basically, we are below the usual difference, okay? Because the difference is of increasing terms. Well, and what we see is that here, using appropriate dissimilarities, appropriate properties for the functions, we do recover shocked integrals. Again, not all shocked integrals are recovered in this way, okay? We are not telling that. What we are telling is that at least some of the shocked integrals are recovered. Okay, so again, there is an unending intersection between this class of functions and the class of shocked integrals, which means that maybe they provide an interesting extension of the results provided by the shocked integral, allowing us to play a bit more because of that result that can be mimicked here, okay, to recover the functions when we know what the result should be. Okay, that's important because that's something we cannot do with the shocked integral. Okay, that's a possible way of avoiding the need of just choosing the parameters in a completely aleatoric way. We can start from the results and try to go to the fashion function. And what are we going to do for the application? Well, I'm going to explain fast, but it's very easy. The first part of the application, okay, there are many more, is just a very simple result. We want to reduce a window of pixels, an image. That's all. So we consider a window, we have a given number of pixels, and we want to reduce its size. How can we do this? Okay, we can divide the image in windows and of the same size, okay, non-overlapping. And then we can use some aggregation, in this case, the functions we are considering, okay, just to reduce each window to one single representative value. Okay, then we have reduced the image. We have many ways of doing this. We can use any aggregation functions we want to use. Perfect. No problem in that sense. But how can we know if the reduction is good or not so good? What we can do is just we have different reductions and we make them return to the original size using always the same method. Okay, let's say, for instance, linear interpolation, whatever. Okay, some method that we know how it interacts with the methods that we have used for the reduction. Okay, and we see which of the reconstructed images is the most similar one to the original one. Okay, of course, this means that we are going to use a similarity, but here there is no trick in the sense that choosing a similarity just to make something work. In fact, we are going to use, for the definition of the shocked-inspired integrals, these two dissimilarities, okay? We are not, we have proof with many more, but just for explaining, this is enough, okay? Because what's interesting is that we are going to consider for the shocked-inspired the functions are going to be chosen between all these functions here. Okay, as you can see, we are not choosing strange operators. We have not even tried to get an operator which is the best one. We have not done here that process of seeing which are the results expected and then trying to get the function set. No, we just want to see if this method actually can work. And we have these results. What is the good thing about this table among all these numbers? In general, if we use for reducing the windows, the average, we get the best results. But in some cases, the Deschochet-inspired, well, provides a result which is not so bad. Okay? You can say, okay, these are not very good results because the Deschochet-inspired at the end is just getting the best result in one case for the salt and pepper noise. Okay? Observe that we have just taken the easiest function. Okay? We have not tried to optimize the functions. What? But let's take this to the real life. Let's take this to pooling. Let's take this to neural networks. Okay? Which at the end, what we are doing is exactly that. Make a reduction, the means of the pooling, to see what happens. And here, the results start to be better. Again, the average, in general, is the one that works better. But in some more cases, the Deschochet-inspired, okay, that Deschochet pooling combination in the last column provides the best results. Okay, that means, again, I am using the easiest function. We have not even tried to optimize them. We get good results. That seems that this approach, at least, is promising. Okay, we are now continuing with experiments. Okay, here there are a lot of people, Joaquin Arellano, Alfonso, they are working on this. Okay, we are getting interesting results. Okay, but even the first approach is promising. Okay, so at least it seems that the construction that we have done can make some sense. Okay, so basically, I hope I have convinced you. If Humberto was here, he would have convinced you, surely. Okay, but I hope that I have also been able to convince you that these approaches open new ways that can be interesting for research and for getting a new way of tackling with problems with a lot of data, okay, trying to optimize the fusion methods. Okay, thank you very much.
Okay, so as usual, Irina will start, Bernard will continue, okay?
Oh, my questions are up. The budget.
Okay.
Okay, thank you. Yeah, thank you. Very interesting. My question is about complexity. Very simple question. Yeah, because actually, when you are performing various kind of integrations, right? Yeah, so with a restricted domain, yeah, what you are extracting is some average value of the observing function, right? And then the neural, so I'm not surprised, yeah, looking at your neural network improvement in a certain case, yeah, because neural network starts, yeah, from this particular, say, approximation, yeah, the first one, and then it somehow recomputes, yeah, the weights, and when the weights are recomputed, your Choquet integral, whatever integral, yeah, disappears actually, yeah, because weights are exactly about how we integrate, yeah. However, another parameter comes into play, and this parameter is complexity, yeah, because yeah, you spend certain efforts, yeah, in order to provide your neural network with the initialization, yeah, and as I said, as well as other methods. So can you compare methods from that point of view? Thank you.
Yes, we can compare them, and in fact, I have just discussed here the part of pooling, as you say, we are losing this information when we learn the new weights and all that, but we are also trying to use all this in other kind of neural networks, for instance, in LLM, okay? using the Shocked integrals in all the steps, what you need to make the function, okay? And in this way, trying to learn the functions somehow, just parameterizing them, and trying to learn them during the process of learning. And we hope that in this case, we will be able to compare. We don't have the results for the moment, okay? But we think that probably we will get promising results, okay?
Bernard, you can.
No.
No? Okay. Somebody else? Of course, typical question when something is done with Shock integral, and what about Sugeno integral? The same ideas only
Yes.
adapted in this.
We are also working in the Sugeno integral because you can do something similar to these things, okay? Something also that is developing in the group right now. So
And the other related question is, of course, once we have Shock integral, which works on either 0, 1 interval or 0, infinity, we go to bipolar.
mhm.
We have several types, at least 4 types of bipolar extensions of Shock integral. How it can work here?
I think it can work. We have not tried, but I think it can work probably. It's probably a good idea to try to do.
Because maybe for some types, yes, for some times, no.
Yes.
Of course, these 2 basics are which are standard Shock integral as proposed by Denneberg and Schiposh integral as proposed by Schiposh. But there are also some other types for bipolar scale. So maybe it.
No, it's a good idea just to try because I think it can provide good results in some problems at least, yeah.
Somebody else wants still ask something or tell something? If not, thank you once more. And the coffee break is, I hope, waiting for